You know that feeling when you open a really dense article, maybe a foundational text or an encyclopedia, and you just know you're going to need a guide to even get through the first page?
Yeah.
We're all just swimming in this complex information, and the real challenge is figuring out what's important, what the words even mean, and how it all connects.
And that is exactly what we're trying to do here. We've taken a deep cut from an authoritative cognitive sciences encyclopedia, and we're going to do a rapid-fire tour through some of the essential concepts, specifically the ones starting with U and V.
Right, so what's the mission today? It's really to give you that shortcut to get you informed on, what, 7 really powerful, complex ideas?
It is. And this particular section, from U to V, is just fascinating because it brings out these 3 sort of core tensions in cognitive science.
Right.
First, you've got this constant push for computational precision, in AI, things like uncertainty and utility theory.
The hard math.
The hard math. Then you have the messy, stubborn reality of human language. Vagueness, linguistic universals.
And the third.
The third is this old philosophical dream, this struggle to unify all of scientific knowledge, the unity of science.
So we're balancing the mathematical with the wonderfully human. I love it. Let's just go alphabetically and see where that takes us. And we're starting not with a computer, but with our own language. Linguistic universals.
Okay, so linguistic universals are basically the constraints that limit how different languages can be. They're the features, the strong tendencies that are shared by all, or at least most, of the world's 7,000 or so languages.
They're like the deep rules of the road for grammar.
Exactly.
But the big question for psycholinguistics has to be, why? I mean, what's enforcing these rules across languages that never even came into contact with each other?
And one of the biggest reasons is surprisingly simple. It's processing constraints. Our brains just struggle to interpret certain sentence structures.
And those limitations actually get baked into grammar everywhere.
Right.
Okay, this is where it gets really interesting. Let's take a self-embedded construction where you stick a clause inside another clause.
The classic example.
Yeah, the source gives us this one. The man that I saw caught took the apple. When you say that, you can physically feel your short-term memory just buckling.
It's a nightmare to parse.
Yeah.
Our working memory just can't track that many nested dependencies. But here's the cool part. If you just tweak the structure a little bit, maybe use the passive voice.
So you're not layering them so deeply.
Exactly. It becomes perfectly clear. The apple was taken by the boy that was caught by the man that was seen by me. It's still a complex idea, but it's organized in a way our brains can actually handle. And that processing hurdle, that's what shapes word order globally.
So our own mental bandwidth is literally shaping the structure of language. But you said universals also come from the function of language, not just the cost of processing it.
Absolutely. Take the universal rule about reflexive pronouns, words like myself, himself.
Okay.
The rule is, if a language has distinct reflexive pronouns for I and you, it must also have them for he and she. You never find a language that does it the other way around.
That seems kind of arbitrary. Why couldn't a language just have himself but not bother with myself?
It all comes down to pragmatic necessity. I mean, first and second person pronouns I and you, they're already fixed by who's talking. If I say I hit, there's no ambiguity. So marking it as reflexive is often just redundant.
But with the third person.
That's where all the ambiguity lives. If I say he hit him, you, the listener, need to know, are we talking about one person or two?
So you need that distinction. You need he hit himself versus he hit him just to keep the references straight. So the place where clarity is needed most is what drives the universal rule.
Precisely. It's a fantastic example of function-shaping grammar.
That is a perfect segue from the limits of our language to the formal systems we build to manage information. Let's talk about uncertainty.
Right. Uncertainty is really the other side of the coin to information. It's intrinsic to any knowledge system. It comes from inaccuracy, from incomplete data, and yes, from that linguistic imprecision we were just talking about.
And since we can't get rid of it, AI and cognitive science are, well, obsessed with trying to reason under uncertainty. And probability is the big one.
It is. It's the best-known formalism, that degree of belief from 0 to 1. But it's not the only tool. There's a whole ecosystem of alternatives, like certainty factors, which are more of a heuristic, or things like Dempster-Shafer belief functions, which actually use a range of numbers to represent ambiguity or even total ignorance.
When people talk about probability, there's always this kind of philosophical split, isn't there, between two camps?
Yes, the frequentist view
Yeah.
and what's called the personalist or Bayesian view.
Okay.
A frequentist thinks probability is objective. It's the long-run frequency of something happening over many, many trials. The Bayesian view is more subjective and, frankly, a lot more practical for building intelligent systems.
How so? What's the practical difference?
The Bayesian view defines probability as your subjective degree of belief, based on everything you know right now. Think about it like this. The probability of a fair coin coming up heads is a frequentist 50%. But the probability that a certain candidate will win an election, that's Bayesian. It's based on your synthesis of polls, history, everything you know.
And your probability might be different from mine.
Exactly. And in AI, this kind of uncertain knowledge is often visualized.
Right, through belief networks.
Yes. Judea Pearl's work on Bayesian networks gives us this really intuitive, graphical way to map out how the probability of one thing affects the probability of another. It's how you manage that complexity.
But we're right back to the language problem. If I tell a system the river is wide, the word wide is vague.
And that's the split. A probabilist would say, get rid of the vagueness first and tell me the probability the river is wider than 50 meters.
Whereas a physicist theorist would say, no, that imprecision is part of reality. We have to model it.
Exactly. They'd represent a linguistic variable, like wide river, with what's called a membership function. A 100-meter river gets a membership of 1 in the set of wide rivers. A 5-meter river gets a 0. The borderline cases are somewhere in between.
So we're building these perfectly rational, precise models in AI. But when we look back at ourselves, there's a huge problem with descriptive validity. Humans just don't think that way.
Oh, not at all. The work by Kahneman, Slovic, and Tversky was just landmark. It showed that our judgment systematically deviates from these probabilistic rules. We use mental shortcuts, heuristics that lead to all sorts of biases.
So we're flawed reasoners. And yet for AI, we still prefer to build systems based on pure rational axioms rather than trying to copy our own messy brains.
That's the core tension. And the whole reason we care about this is because uncertain reasoning is what lets us make good decisions, which gets us to utility theory and, believe it or not, to the unity of science.
Okay, wait, that feels like a sharp turn. If we're so systematically irrational, where did this grand idea of a perfectly unified rational science even come from?
That's the perfect question. Unity of science is this really ambitious, long-held view that all scientific knowledge should be integrated. And, cognitive science itself, blending linguistics, AI, psychology, is kind of a working example of that, at least on a small scale.
The modern push for this came from the logical positivists back in the 30s and 40s, right? People like Carnap. They saw physics as the ideal and wanted to unify everything through reduction.
That's right. And their first attempt was reduction at the level of observation. The idea was to reduce every scientific claim back to some basic class of physical observational reports. This idea, heavily influenced the behaviorist movement.
But it didn't really pan out.
No, it failed. They could never develop a coherent logical analysis of what a pure observation even was. So they shifted. They moved to the reduction of theory.
So taking a higher level science like psychology and trying to reduce its laws to a more basic one like neuroscience.
Exactly. But to do that, you need these perfect translation laws to connect the vocabulary of both fields, and then you have to derive the higher laws from the lower ones.
That sounds incredibly difficult. Maybe impossible.
It is. And it ran into serious objections because those perfect translations just don't really exist most of the time.
So if that top-down grand reduction failed, what other models for bringing science together came along?
Well, you saw two main alternatives. One was the search for common theoretical frameworks. Think of things like cybernetics, which looked for general principles like feedback loops that could apply to biology, engineering, social systems, everything.
And the second idea sort of gives up on having one big framework.
Right, that's interfield theories. The idea here is to have theories that just directly link phenomena in two different fields without saying one is more basic than the other.
Can you give a successful example?
The modern analysis of aphasia is a great one. You're creating direct links between specific deficits in syntax or semantics, which is linguistics, and localized brain damage, which is neuropsychology. Neither field could get those insights on its own.
So it seems like the modern version of Unity is less about some grand philosophical project and more about just sharing your tools.
Absolutely. Cognitive neuroscience is the poster child for this. It's all about integrating behavioral data like reaction time with imaging tools like fMRI. The grand dream might have faded, but this local integration, this network of shared tools and problems, That's happening every day.
Okay, let's circle back to those computational demands we saw in uncertainty, especially how a system can learn from tons of data without a human labeling everything. This is unsupervised learning.
And this is so critical for both AI and neuroscience. Unsupervised learning is all about how a system can learn to find patterns based only on the statistical structure of the data itself. The key thing is there's no teacher, no explicit target outputs.
Which sounds a whole lot more like how our brains actually work.
It's considered much more common, yeah. I mean, think about your eye. You have 100 million photoreceptors constantly firing. Almost none of that input comes with a label saying this is a cat or this is a table. Unsupervised methods are how we model the brain extracting the actual objects and causes from that raw flood of data.
So if there's no teacher, how does a system figure out what the right features are to pay attention to?
There are two main strategies. The first is density estimation, or what are called generative models. Essentially, the system learns to build a statistical model of the input. It learns how to generate new samples that look like the data it's seen.
What's a real-world example of that?
Clustering is the classic one. You use a model like a mixture of Gaussians, you feed it a bunch of data points, and the system automatically figures out where the groups, the clusters are, their centers, their shapes, without ever being told which point belongs to which group.
And what's the second approach?
That's feature extraction. So instead of trying to model the entire data distribution, you just define what makes a feature good or interesting, and then you design a system to go find those.
What makes a feature good in that sense?
Often, it's having statistics that look different from random noise. Most random projections of data look Gaussian, like a bell curve. So a technique like projection pursuit specifically hunts for the projections that are highly non-Gaussian. Those are the ones that reveal the interesting, hidden structure in the data.
That's a fantastic way to think about organizing knowledge without instructions. Now let's connect that power back to human action with utility theory.
Right. Utility theory is all about the measurement and representation of our preferences when we make rational decisions. Utility is the scale we use for that measurement.
And this is a very old idea, isn't it? It goes back to the 18th century, to Daniel Bernoulli.
Absolutely. He resolved the famous St. Petersburg paradox by showing that our preference isn't just about raw monetary value. He argued that utility is logarithmic, meaning an extra dollar is worth less to you the more dollars you already have.
And we have to distinguish between two kinds of utility here.
We do. For choices under certainty, where the outcomes are fixed, we use ordinal utility. The scale only has to represent the rank order of your preferences. But as soon as you introduce uncertainty, like in a gamble, you have to calculate expected utility.
And that's different because
Because it requires what's called the Independence Axiom, and it forces the measurement scale to be cardinal. The intervals on the scale have to be meaningful, which is what allows you to calculate a true expected value. This became hugely important when von Neumann and Morgenstern used it as the foundation for game theory.
it's the cornerstone of decision theory, but just like with probability, humans often don't follow the rules.
They don't. The LA paradox showed clear cases where people violate the expectation principle. And that's what led to really important alternative theories like Kahneman and Tversky's prospect theory, which tries to model how we decide based on perceived gains and losses from a reference point, not just absolute outcomes.
And a key concept in all of this is risk aversion.
Risk aversion is simply the tendency to prefer a sure thing over a gamble with the same expected value. If you're offered a guaranteed $50 versus a 50-50 shot at 100 or nothing, and you take the 50, you're risk averse. And this is why AI designers are now moving beyond simple goals and are actually encoding these detailed utility functions into their agents.
Okay, our final entry brings us full circle right back to the limits of our language and thought. Vagueness.
Vagueness is what describes words like tall, red, or heap. They all have borderline cases, situations where you can't say the word is clearly true or clearly false. They have fuzzy boundaries.
And this leads to the classic philosophical problem, the Sorites paradox, the paradox of the heap.
Exactly. If you have 1,000 grains of sand, it's a heap. Take one away, it's still a heap. Since one tiny change can't possibly matter, you repeat that logic until you reach the absurd conclusion that one single grain of sand is also a heap.
It's important to remember that this isn't the same as ambiguity.
Absolutely not. A word like bank is ambiguous. It has two clear, distinct meanings. A word like heap has one meaning, but its boundary is fuzzy.
So how do philosophers try to solve this paradox? There are three main views, right?
Right. The first is the most conservative one. It's the epistemic view, It holds on to classical logic. Every statement is either true or false. It just says that for borderline cases, we are ignorant of where the sharp boundary actually is. The line exists, we just can't see it.
So the argument that removing one grain makes no difference is just false. We just don't know which grain makes it false. What's the next view?
That's degree theory, or fuzzy logic, which we touched on earlier. This view throws out classical logic and introduces a whole spectrum of truth values from 0 to 1. Borderline cases have an intermediate truth value. So the premise that removing one grain doesn't change the heap status is considered only almost completely true. And over thousands of steps, that tiny departure from truth adds up and dissolves the paradox.
And the third solution?
Supervaluationism. This one treats vagueness as a kind of semantic indecision. A statement is only true if it's true on all the possible ways you could make the vague term precise. This lets you keep classical truths, like a person is either tall or not tall, while still saying a borderline case is neither true nor false. When you look back across all 7 of these concepts, the real through line is this constant struggle. It's the struggle to reconcile the demands of these highly formal systems, all that proficient in probability and utility, with the messy, subjective, often fuzzy reality of human cognition. And cognitive science really exists to bridge that gap.
That tension is so clear. We saw how something as simple as our brain's difficulty with a nested sentence actually ends up constraining every human language on the planet. Next time you make a big financial choice, think about your own risk aversion function. Are you thinking in terms of raw dollar value or the deeper utility that money represents for you? And how might an AI be trying to model you using something like a mixture of Gaussians?
And we really encourage you to explore that fascinating overlap between utility theory and the descriptive theories, like prospect theory. It's a great window into how behavioral economics is informing our models of decision-making.
Thank you so much for taking this deep dive with us. We hope this shortcut has left you feeling well-informed and ready to explore these foundational concepts even further.